Lecture 31 will start out by reviewing a little bit of the chemistry that we just started in the last class, that is starting with chapter 8 in alkene addition reactions. And once we review a little bit of the chemistry, that is the reaction and mechanism, we're going to talk about two new types of reagents that can add to alkene double bonds. And as you'll see, they use very, very similar principles. So in the last class, we started talking about a new set of reactions that are called addition reactions. Specifically, we're talking about alkene additions, and in general, we often call these electrophilic addition reactions. For these reactions, the alkene pi bond is going to be our nucleophile, and our electrophile is going to be a variety of reagents as we go through this chapter. And the only electrophiles that we've discussed so far are the acids, Bronsted acids, such as HCl, HBr, and HI. So using what we have presented in the last class as far as the mechanism, predicting the outcomes, stereochemistry, regiochemistry, use this example below and draw a mechanism that shows how to predict the reaction product or products. Be sure that to include the configurations of any stereocenters if any form in this reaction. So I would start out this mechanism by redrawing the HBr to emphasize the sigma bond between the hydrogen and bromine. And then the first step of this mechanism is the attack of the pi bond onto this electrophile. Remember that the hydrogen of the acid is the delta positive, and so that is the atom that gets attacked by the nucleophile to create a new carbocation intermediate. This new intermediate is actually a relatively stable carbocation. It's tertiary. And then the final step of this reaction is going to be attack of the nucleophile, which is now going to be the bromide, onto this electrophilic carbocation to create a new structure where we formed a sigma bond between the carbon and bromine. Now that we've identified the product that forms, we should ask ourselves, did we form a new stereocenter in this process? Does the product include a new stereocenter from where it started? And the answer in this case is certainly yes. We have a central carbon that has a methyl, an ethyl, and a propyl group, as well as the bromine atom. So we did create a new stereocenter in this reaction. So we need to now represent this in terms of what is the outcome of this process. Remember that carbocation intermediates, the carbon itself is not a stereocenter because it's sp2 hybridized. But once the bromine adds to that and creates a new stereocenter, we should expect an equal mixture of the two configurations at that one position. So for this, instead of drawing the structure as I have here, it will be best to draw this as showing the configurations. So I'm going to go ahead and draw both of the configurations and assign the stereochemistry of each of the configurations. And that is the complete answer for this problem. What I do like about this is that it emphasizes first the mechanism, that is the pi bond attacking the acid, forming a carbocation intermediate, or the intermediacy of a carbocation intermediate, and then finally the last step is forming the sigma bond. And in this case, this is one example where we did create a new stereocenter. I would like you to take that specific example and contrast that with the one from below. It looks like a very, very similar reaction, except in this scenario I have replaced the HBr with sodium bromide. So in this specific example, there is no reaction observed. That is, there's no addition process that's observed. And so I want you to think a little bit about why this doesn't give us an addition product. What is the difference between this example and the example at the top? And the answer for this is to think about the reaction mechanism. What happens in this process? It should form a carbocation intermediate, which does require a strong acid. There are no protons in this reaction with sodium bromide. So since it does not include a strong acid, no carbocation intermediate can form, and therefore no product, no addition product can happen. And so that's a really important element to the examples that we're going to talk about today. They require the use of very strong acids to form carbocation intermediates. So the next type of electrophilic addition that we're going to cover right now is using a different type of electrophile. And this is going to include water as a reactant for these reactions. The overall process is shown here. It involves the addition of water to a pi bond to add both an OH group and a hydrogen to the alkene. And so we actually call this reaction a net hydration reaction. So we're going to add water to the double bond. We're going to hydrate the double bond to form new alcohol products. A theme for this reaction is very similar to the addition of mineral acids. That is, it does require the use of a proton or a strong acid catalyst. And so the most common one that we're going to see is adding sulfuric acid to water. I think everybody should be familiar with sulfuric acid from prior chemistry classes. Sulfuric acid is an example of a very, very strong Bronsted acid. And as we're going to see, the mechanism for this reaction involves very similar steps to what we just covered: proton transfers, carbocation intermediates, and then a nucleophilic attack on the carbocation. So let's go ahead and go through the reaction mechanism for this reaction. So the first step that's going to happen is we're going to assume that we're going to have the presence of H3O plus in our reaction. So H3O plus is the acid form of H2O, and this actually forms from the interaction of sulfuric acid with water. I'm going to briefly show you below what's exactly happening with this, but for our understandings, we should assume that there's going to be H3O plus and H2O in this reaction. And between the two, H3O plus is definitely the much stronger acid. Okay, so now that we've shown how H3O plus forms in this reaction, for your purpose, or for your drawing reaction mechanisms, you should just assume that H3O plus is present, because anytime we have a strong acid dissolved in water, it forms H3O plus. Okay, so we have our reactant, our nucleophile, which is the pi bond of the alkene, and that's going to attack the strongest acid in the reaction, which is H3O plus, and this will create our carbocation intermediate plus H2O. Now once these two intermediates form, we are seeing that we're forming the same type of carbocation intermediate that we did in the previous reaction. We also know that you've seen water being used as a nucleophile in the past. So water can now attack the nucleophile, and that creates a new product where now the oxygen has a formal positive charge again. The last step of this process is removal of that proton, a final proton transfer that uses water to regenerate the acid. One final thing to mention before moving on is the fact that once we formed our carbocation intermediate, I used water as the nucleophile to attack the carbocation. One thing that I did not use is I did not use OH minus or hydroxide. Right? So you'll notice that for these conditions, they're under strongly acidic conditions. And under strongly acidic conditions, hydroxide is not present. It's not going to be applicable to this reaction mechanism. So under acid catalyzed conditions, do not draw strong bases like hydroxide. So hopefully you observed from the previous mechanism there's a lot of parallels between the addition of water and the addition of, say, HBr. Both are acid catalyzed processes. They go through carbocation intermediates and they result in alkene addition products. So because of these parallels, you should expect a number of factors for these types of reactions. That is, you should expect Markovnikov regioselectivity. That is, the nucleophile should attach to the most substituted position. In this case, the nucleophile is going to be OH because the nucleophile is ultimately water. Whenever we do form a new stereocenter, you should also expect that the stereoselectivity should be an equal mixture of the two configurations, at least of the position that's forming. And the last thing is, because of the intermediacy of carbocations, we would expect rearrangements to happen. So all three of these factors are really consequences of the fact that there are carbocation intermediates for these reactions. So I give you one more example below, and what I would like you to do is show how both of these reaction products form, and also if there's a mixture of stereoisomers. So pause the video and draw the mechanism for this process. One thing to keep in mind before you do this is you can just go ahead and assume that H3O plus is already present, although you'll typically see it written as H2SO4 and water for typical examples. Okay, so you have the pi bond and your electrophile, which is H3O plus. First step is the proton transfer. Again, that you might find it helpful to draw the dashed line between the carbon and the electrophile. That's why I'm doing this here. You don't have to, but I think it's helpful to determine the connectivity, right? So the pi bond attacks the proton, and it looks like this for the proton transfer to form a secondary carbocation. Again, you don't have to draw the hydrogen. Maybe I will here just to show you where it ends up. But you'll see that as I start going through this chapter, I'm not going to demonstrate where all the hydrogen atoms are. Okay, so we have the secondary carbocation. This is where the nucleophile can capture that. We have just neutral water, which is our nucleophile, so that will attack the carbocation, and that will form a new formally charged product. And then a final proton transfer will give you the reaction product, the first reaction product shown. Do keep in mind that in this reaction we have formed this new stereocenter with the OH group, the alcohol, and because of that we would expect this to be an equal mixture or racemic. And the best representation of this is the two separate enantiomers shown, and they're going to be in equal mixtures. Okay, so that is the first product. How does the second product form? We need to go back to our carbocation intermediate and actually work from this structure to show how the rearrangement occurs. So I redrew the carbocation just to make this hydride shift very clear. But once we have the carbocation, we have a neighboring hydrogen that's attached to a tertiary position. So this hydrogen atom can migrate over. Remember, this is called a 1,2 hydride shift. And this will create a new, more stable carbocation, which is tertiary. Now with the tertiary carbocation, the final steps of the mechanism mirror that from above. Water attacks the carbocation to form a formally charged structure, and then we lose the last proton through a simple proton transfer. Note that in this case, the product that forms does not form a new stereocenter, or a new stereocenter is not created. The final product is achiral, so there's no question of stereoisomers that form. And so that's how the rearrangement product forms. So this is just to serve as an example to show you how these reactions parallel that of the HX additions, but also there should be a lot of similarities to things that you would have seen for the SN1 types of reactions from earlier in the semester. So this slide shows an example of the reaction taken from your textbook, at least an example taken from your text that goes through exactly what we just showed through two examples of hydrations of alkenes. First step is our proton transfer, and then you get a nucleophilic attack of water, which is our nucleophile, and then a final proton transfer to form the alcohol product. So I have an example of 3 different substrates shown at the bottom left of the slide, and I want us to try and explain or understand the difference between the rates of these reactions. That is, the simple alkene in the first example has a relative rate of 1, which is, I guess, a representation of our normalized value. The alkene in the second example is 10 to the 6 times faster. And all that we did was add in a methyl group to this structure. And then finally, adding one more methyl group to the alkene makes the rate go even faster, almost 10 to the 11th. So what is the reasoning behind this difference in rate of hydration for these 3 substrates? So let's think about this in the context of the reaction above, right? So what types of, for example, the first step in this forms carbocation intermediate. So what are the structures of the carbocations that you would expect from this reaction? Pause the video and draw the carbocations for each specific example. Okay, so here is what you should have gotten for your 3 carbocations. The first one is going to be a primary carbocation, the second is a secondary, and the third is a tertiary carbocation. Now we know something about carbocation stability, and as we're going down this chart here, or this list of examples, you know that tertiary carbocations should be among the most stable. You can also see that the tertiary carbocation is the fastest example in this list. So carbocation stability seems to have a pretty large impact on the rate of this reaction. So here's an energy diagram that represents the first step for each of these individual substrates, and I've organized it based off of the stability of the carbocation intermediate. You should note that this energy diagram, or at least the first step of this, represents very much like we would have seen for an SN1 reaction. That is, the more stable the carbocation is, the lower in energy the transition state is. And this is an example of the Hammond postulate, or an application of the Hammond postulate. What it suggests about this multi-step reaction mechanism above, if we count the total numbers of steps, there's 2. The first step is the proton transfer, second step is nucleophilic attack, and the third step is a proton transfer. If we have 3 steps, one of them has to be the slow step or the rate determining step of the reaction. So in this example for hydration reactions, or we can also say in general HX additions, the rate determining step is going to be formation of the carbocation intermediate. That is why overall we see a difference in rate for different substrates. So tertiary substrates, or I should say substrates that create more stable carbocations, will in general react much faster for these electrophilic addition reactions of HX and water.